Welcome to this pre-recorded lecture on causal effect definitions based on potential outcomes. In this lecture, we'll go over individual level causal effects, average level causal effects, and we'll end with some take-home messages. By the end of this lecture, you should be able to define individual level causal effects in terms of potential outcomes, and you should be able to define average level causal effects in terms of potential outcomes. Let's start with individual level causal effects. Most epidemiologic studies are set up to assess potential causes of disease occurrence. So a lot of epidemiologic studies are set up to answer questions like, does exposure A cause health outcome Y? And in an ideal setting, we would actually like to know if an exposure caused a certain health outcome at the individual level. So to provide an example of this, let's suppose that Ruth smoked cigarettes between the ages of 18 and 72. Let's also suppose that Ruth had a stroke at the age of 72. Now we may wonder, was it the cigarette smoking that caused the stroke? In other words, when can we conclude that Ruth's cigarette smoking caused the stroke? Another example. Let's suppose that Peter received 2 doses of the measles vaccine as a child and has never had the measles by the age of 30. Now we may wonder, was it the vaccine that helped prevent measles in Peter? So in other words, when can we conclude that Peter's vaccine caused the absence of measles? Causal effects can be defined using the counterfactual or potential outcomes framework. A causal effect in each of these frameworks is defined based on the comparison of 2 counterfactuals or 2 potential outcomes. From here on out, I'll be using the term potential outcomes, but at any point you can interchange that with the word counterfactuals. To determine cause and effect, we need to compare 2 potential outcomes. The first potential outcome is the outcome if individual I is exposed during time period T. The second potential outcome is the outcome if individual I is not exposed during time period T. The causal effect is then the difference between these 2 potential outcomes. We would conclude that there is no effect when the outcome is the same across the 2 potential outcomes. So in other words, we would conclude that there is no causal effect if in both potential outcomes the individual ended up developing the outcome of interest, or if in both potential outcomes the individual ended up not developing the outcome. We would conclude that there is an effect when the outcome differs between the 2 potential outcomes. So for example, if the individual did end up developing the health outcome when exposed, but not when not exposed, or vice versa. Now let's revisit Ruth's case. Remember that Ruth smoked cigarettes between the ages of 18 and 72 and had a stroke at the age of 72. Now let's suppose that we live in some magical world where we actually know the other potential outcome as well. So let's suppose that if Ruth did not smoke cigarettes between the ages of 18 and 72, that she would not have developed a stroke by the age of 72. So based on these 2 potential outcomes, would you conclude that cigarette smoking caused the stroke? Yes. In this situation, we would conclude that cigarette smoking caused the stroke. Because if we compare the 2 potential outcomes, one in which Ruth smoked cigarettes and the other one in which Ruth did not smoke cigarettes, then the outcome was different. So when Ruth smoked the cigarettes, she developed a stroke, but this didn't happen in a scenario where she did not develop the stroke. Of course, we do need to assume that the only thing that differed between these 2 potential outcomes was the exposure, so everything else was equal. Now let's suppose that Peter received 2 doses of the measles vaccine as a child, and he never had the measles by age 30. Suppose that if Peter had not received the 2 doses of the measles vaccine as a child, he would also not have gotten the measles by age 30. The question that we might ask ourselves is, did Peter's vaccines cause the absence of measles? The answer is no. In this case, across both potential outcomes, Peter did not end up developing measles by age 30. So in this case, we cannot conclude that it was the 2 doses of the measles vaccine that prevented measles in Peter. Now that we have seen some examples of how potential outcomes can be used to determine cause and effect, let's introduce some potential outcomes notation. Throughout the remainder of this lecture, I will use Y to denote the outcome, and I will use A to denote the exposure, where the lowercase italicized a represents a specific value of the exposure. And the values chosen for the lowercase of a represent what we call the causal contrast. So those values are the 2 values that we aim to compare with one another to determine if there is an effect of the exposure on the outcome. So now let's use Y and A to denote the individual level potential outcomes. So Y A equals 1 represents the outcome when individual I is exposed during time period T. And Y A equals 0 represents the outcome when individual I is not exposed during time period T. So in this case, A equals 1 refers to the exposure status, and A equals 0 refers to a status in which the individual is not exposed. So in other words, A equals 1 and A equals 0 represents the 2 values of the exposure that we're comparing with one another. So this is what we call the causal contrast. If we have a binary exposure variable that consists of 2 levels, then it's relatively easy to define A1 and A0, because A1 would be one level of the exposure and A0 would be the other level of the exposure. Now, if we have a multi-categorical exposure or we have a continuous exposure, then we'll need to pick 2 values that we'll be comparing to one another. So if, for example, we use blood pressure as our exposure variable, we would have to pick 2 values of blood pressure to compare to one another. Now that you are familiar with the individual level potential outcomes notation, we can use this notation to denote the individual level causal exposure outcome effect. And the individual level causal exposure outcome effect is the difference between YA equals 1 and YA equals 0. So if these 2 potential outcomes differ from one another, then we would conclude that there is an effect of the exposure on the outcome. And if these 2 potential outcomes are the same, then we would conclude that there's no causal effect of the exposure on the outcome. Going back to Ruth's case, Ruth's stroke status by the age of 72, if Ruth did smoke cigarettes between the ages of 18 and 72, would be denoted as YA equals 1. And Ruth's stroke status by the age of 72, if Ruth did not smoke cigarettes between the ages of 18 and 72, would be denoted by YA equals 0. So again, we can then compare these 2 potential outcomes. If Ruth developed stroke under both potential outcomes, we would conclude that the cigarette smoking was not the cause of the stroke. But if Ruth did develop the stroke when smoking cigarettes but not when not smoking cigarettes, we would conclude that it was the cigarette smoking that caused the stroke. In Peter's case, YA equals 1 represent Peter's measles status by age 30 if Peter did receive 2 measles vaccines during childhood, and YA equals 0 represent Peter's measles status by age 30 if Peter did not receive 2 measles vaccines during childhood. So to summarize, individual level causal effects are defined in terms of differences in potential outcomes or counterfactuals. Potential outcomes represent the outcomes that will be observed under different levels of the exposure. And YA represents the outcome observed under a specific exposure value A. So we can define YA equals 1 and YA equals 0 to compare the outcome under 2 different exposure values. Now let's continue with average level causal effects. Probably by now you're thinking, those individual level potential outcomes are all fine from a philosophical point of view, but in practice we're never going to be able to observe both of those potential outcomes for the same person at the same time. And you're absolutely right. That's what we call the fundamental problem of causal inference. Again, it is impossible to observe both potential outcomes for the same individual over the same time period. And because it is impossible to identify individual level causal effects, in practice we often aim to estimate average level causal effects using data from a population of individuals. When our interest is in average level causal effects, we need to make sure that we adapt our notation to reflect that we're looking at the average level. Y A equals 1 still represents the outcome when exposed, and Y A equals 0 still represents the outcome when not exposed. The change that we're making to the potential outcomes notation is that we have now put each of these potential outcomes in a bracket preceded by E. And E here stands for the expected value. So E is the expected outcome based on a group of individuals. So E Y A equals 1 represents the average outcome if all individuals in the population were exposed during time period T. And E Y A equals 0 represents the average outcome if all individuals in the population were not exposed during time period T. It's important to note here that we're now looking at all individuals in the population being exposed versus all individuals in the population not being exposed. The average causal effect is concluded to be present if there is a difference between these two average level potential outcomes. If the two average level potential outcomes are the same, then we would conclude that there's no effect of the exposure on the outcome. Various measures may be used to measure the average level potential outcomes. If our outcome of interest is a continuous variable, for example blood pressure, fasting glucose levels, serum cholesterol levels, then means can be used to measure the average level potential outcomes. E Y A equals 1 is then the mean outcome if all individuals in the population were exposed, and E Y A equals 0 is the mean outcome if all individuals in the population were not exposed. We can then define the average level causal effect as the mean difference. So it would be the difference between those two means observed if all individuals were exposed versus if all individuals in the population were not exposed. If our outcome of interest is binary, for example, disease presence or disease absence, then we can use probabilities to measure the average level potential outcomes. If we're looking at probabilities instead of means, we can change our potential outcomes notation a little bit more. If we take a look at the two potential outcomes notations on the slide, we see that we now use PR instead of E. And PR here stands for probability. Another thing that we changed about the potential outcomes notation is that within the bracket it now says Y equals 1, which means that we're specifically interested in the probability of observing Y equals 1. So again, if our outcome is binary, where 1 represents disease is present and 0 represents disease is absent, then PR Y equals 1 means that we're interested in the probability of observing the disease. So PR Y A equals 1 is the risk of the outcome if all individuals in the population were exposed. And PR Y A equals 0 equals 1 is the risk of the outcome if all individuals in the population were not exposed. There are now multiple measures of the causal effect that we can use based on these probabilities. If we look at the difference between these two probabilities, then we get an estimate of the risk difference. We can also look at the risk ratio, and we can even compute an odds ratio based on these probabilities. So far, we've seen how we can adapt the potential outcomes notation to denote that we're now looking at average level potential outcomes instead of individual level potential outcomes. Please recall that in the interpretation of these average level potential outcomes, I've been emphasizing the fact that these potential outcomes apply to a situation where all individuals in the population are exposed or where all individuals in the population are not exposed. And this is where we run into a problem again. Because we're looking at a situation in which either everybody is exposed or nobody is exposed, we still cannot observe both EYA equals 1 and EYA equals 0 in practice. In practice, we instead estimate the potential outcomes based on subsets of the population. In other words, a part of the population is exposed and another part of the population is not exposed. And we use these two subsets of the population to estimate the potential outcomes conditional on exposure status. To reflect the potential outcomes that we measure in practice, we need to further adapt our potential outcomes notation. So the average potential outcomes conditional on exposure status would be EY conditional on A equals 1, which is the average outcome among the exposed subpopulation. And then EY for A equals 0 is the average outcome among the non-exposed subpopulation. It's important to note here that we've included this vertical bar in the potential outcomes notation, which means that the outcome is conditional on that specific value of the exposure. So that first potential outcome is conditional on being exposed, and the second potential outcome is conditional on not being exposed. We can change the notation for a binary outcome in a similar manner. So remember, for a binary outcome, we look at probabilities. So here we have the probability of the outcome being equal to 1, conditional on the exposure A being equal to 1. So the probability of the outcome among the exposed subpopulation. And then we have the probability of the outcome being equal to 1 when A is equal to 0. So this is the probability of the outcome among the non-exposed subpopulation. And again, this vertical bar that's now included in the potential outcomes notation means that the outcome is conditional on a specific value of A. So either being exposed or it's conditional on not being exposed. Let's take a look at the average potential outcomes notation in the context of an example. In this example, we were interested in determining if cigarette smoking increases the risk of stroke. So in this example, stroke is our outcome of interest, which is a binary variable where 1 indicates that an individual experienced a stroke and 0 indicates that an individual did not experience a stroke. PRY equals 1 then indicates that we're interested in the risk of experiencing a stroke. So the potential outcome PRY equals 1 conditional on A equals 1 represents the risk of stroke among the subpopulation of individuals who smoked cigarettes between the ages of 18 and 72. The potential outcome PRY equals 1 conditional on A equals 0 represents the risk of stroke among the subpopulation of individuals who did not smoke cigarettes between the ages of 18 and 72. If we observe that the risk of stroke among the subpopulation of individuals who smoked is higher than the risk of stroke among the subpopulation of individuals who did not smoke cigarettes, and everything else was equal between these two groups, then we would conclude that it was indeed the cigarette smoking that increased the risk of stroke. If the risk of stroke is the same across these two groups, then we would conclude that cigarette smoking did not affect the risk of stroke. In practice, any measures that we compute in an epidemiologic study represent association measures. So for example, when we compute a mean difference in an epidemiologic study, it represents an associational mean difference. It's the difference in the mean among those who were exposed and the mean among those who were not exposed. If we compute a risk difference, then it's an associational risk difference because it's based on those conditional average level potential outcomes. So it's the risk of the outcome among those who were exposed compared to the risk of the outcome among those who were not exposed. We can compute an associational risk ratio as well, and we can even compute an associational odds ratio. So far we have learned that average level causal effects are defined based on E, Y, A equals 1 and E, Y, A equals 0. And remember, for each of these two average level potential outcomes, we're assuming that we're measuring the outcome based on a situation where everybody in the population is exposed, so that's for E, Y, A equals 1, or where everybody in the population is not exposed, which is for E, Y, A equals 0. We also talked about the fact that in practice we cannot observe these two average level potential outcomes, and instead we can only estimate E, Y conditional on A equals 1 and E, Y conditional on A equals 2. So in other words, these potential outcomes at the average level are conditional on exposure status. This means that the association measures that we compute based on these conditional average potential outcomes will only equal causation measures if E, Y conditional on A equals 1 is the same as E, Y, A equals 1. And if E, Y conditional on A equals 0 is the same as E, Y, A equals 0. The conditional average potential outcomes will only be the same as the average potential outcomes if the identification assumptions hold. The identification assumptions are exchangeability, consistency, and positivity. So when these three assumptions hold, the association measures, so the measures of the mean difference, risk ratio, odds ratio that we compute in our study, will be equal to the causation measures. To summarize, average causal effects are defined based on a comparison of the potential outcomes when everybody in the population is exposed versus when everybody in the population is not exposed. In practice, we measure potential outcomes for subpopulations of exposed and non-exposed individuals. Therefore, in practice, we use association measures to estimate causal effect measures. Those association measures will only reflect causal effects when the identification assumptions are met. This brings us to the take-home messages. In this lecture, you have learned that causal effects are defined in terms of differences in potential outcomes or counterfactuals. We cannot observe individual level causal effects due to the fundamental problem of causal inference. In other words, we cannot observe both potential outcomes for the same individual at the same time. Therefore, in practice, we aim to estimate population average causal effects, which are defined as the difference between two average potential outcomes. This brings us to the end of this lecture.